Ready to go. Have a good session.
Okay. Well, I'm happy to announce our first invited speaker for CHESS 2021. Carmela Troncoso will give a talk. She's an assistant professor at EPFL, where she heads the Spring Lab. Her research covers a wide range of topics that are essential to enable the development of technology that can be used to build socially responsible systems. Most of our work focuses on analyzing, building, and deploying secure and privacy preserving systems. She has been named 40 under 40 in technology by Fortune in 2020 for her work on contact tracing apps. I think that's where most of us know her from. And she will give a talk about hardware for privacy engineering. So with that, Carmela, the floor is yours.
Thank you very much, Elke, and thank you, Peter, for this invitation. That made me very nervous because, as Elke said, I'm a very privacy person. I'm a not at all hardware person. And when they wrote to me, I said, you got the wrong address. Like, why are you inviting me to give a talk at CHESS? And they said, well, we would really like to have a talk in which somebody brings a new topic and the needs of this new topic from the hardware side. So here is my attempt to produce that, and I hope I have fulfilled what they asked me to do. And I really hope that you find this interesting and it actually inspired you to open your horizons about what kind of hardware you design and design more things that us from the privacy engineering domain can take. I also have to say I'm very sad that CHESS always happens in very exotic places like Japan and things like this. And these guys just invite me today, but it's virtual. But we'll talk about it some other time. So why do we do privacy? Well, what is this privacy thing all about, right? We live in this digital world in which more and more all of our interactions are just dealt by digital things. Well, this conference is one example, right? But we do music, not anymore on CDs, but on Spotify. We talk with our oven to ask the oven to hit before we're going home. We don't ask for a taxi with a hand in the street. You ask for an Uber and so forth and so forth. And all of these technologies, we know that, how they get all of this data, but what we do when we do it. And we start to feel like we live under the big eye of sorrow. And this is uncomfortable. But what we really fear, like in the movie, is not the eye. Nobody was trying to destroy the eye. We were trying to destroy the ring. Because the ring, the thing that gives the power to dominate it all, and that is data. That's what happens when we put our lives on someone, when someone can read our souls, when someone can read what we like, what we do. The next thing we're going to do, and they can predict it, and not only predict it, but then also influence it. And I'm thinking, for instance, about the Cambridge Analytica Facebook scandal, where it was like the first time that all of the fears that privacy advocates had said, like when someone has a lot of your data, they can start controlling and manipulating you, came into place. And well, what happened after that is history. And in the words of Solov, right, parts of what makes society a good place in which to live is the extent to which it allows people freedom from intrusive motives, as I said, from manipulation, for implications, right? Whenever we want privacy, we don't say we want privacy because we don't want people to know our secrets, or we don't want people to know. We just don't want to hear what they have to say. We don't want them to judge us. We don't want them to change us because they know privacy information. So what we really want is to not have the consequences of losing our privacy. And indeed, a society without privacy, in which everything would be known and we would be judged all the time, and we could be manipulated all the time because everybody knows our deepest wishes, would be suffocation. It's not a place where we want to live. So once we all agree, we don't want the ring to be built, we have a goal. The goal is privacy by design. And a while ago, a lot of people back in the 2010s, this was the hype start. Everybody was like, we want privacy, and policymakers started to push this very hard, right? We have here some quotes from the Data Protection Office in Ontario, in Canada, which was one of the first strong proponents of this privacy by design concept. I have here a quote from the GDPR about how, from the start of the system, we need to implement appropriate technical and organizational measures. Have the FTC saying that we should incorporate substantial privacy protection in the practices, and all of those things. And all of these things are great, and we all love them. But you know, as a privacy engineer, and especially when I was working for industry and I had a team and people were reading all of these things, they were looking at me and it was really like, okay, this really feels like this. You know, here is a system, now put the freaking privacy on it. And so with my colleagues, Claudia and Sarah, a while ago, we also started to think about how can we help engineers to move from the circles to the all. And in the beginning, we published a paper that says that it was all about data minimization. What we do is to build systems without data, because the less data that is in the system, the more privacy preserving it is. And this was very celebrated and people like it very much, especially on the policy side, because it was clearly related to data protection regulation principle, the principle of data minimization, and everybody could understand this. But when we were working a bit further on how to articulate what we do to build systems, we discovered that really data is not minimized in the system as a whole. Because whenever we build a privacy preserving system, data still exists. It may exist only in the user device. It may exist encrypted to the server where only the client has the key, or where we encrypt it with some advanced cryptography so that we can make operations with it. We can distribute it over multiple servers. But at the end of the day, data still exists. So just talking about minimizing data is really not a good metaphor to just explain to your engineers how they have to think to actually fulfill this idea of privacy by design. So we went back to the drawing board and to think about more what is it that people that work in academia and privacy do when they design this wonderful privacy preserving system. And we came to the realization that what we actually do is to minimize the privacy risks. And we do that by minimizing the trust assumptions on others. In many places, trust is considered a good thing in the sense that, you know, if I can trust you, that's good. But from a privacy perspective, the least I need to trust you, the more sure I am that you're not going to violate my privacy. And kind of the key here is this on other entities. And this is what kind of differentiates a little bit the kind of things that privacy engineers do more here on the right, on the privacy enhancing technology side, from maybe others, like in the sense of who are we trying to protect from? In general, we're used to this kind of third-party privacy. That's what we have in social networks, where we trust the provider, but then we don't trust other users or other third parties, and we have all of this access control. Right now, we were having this. There was this conversation about Zoom, how we don't trust Zoom. But well, I mean, we need to trust it, and then we trust that Zoom is not gonna broadcast everything we said to others. And because we may don't trust very much, so came the regulatory approaches that try to put some pressure on the provider from the legal side. They would have fines if they end up leaking something and things like this. But actually, from a privacy perspective, we would like to live here, the place in which we don't trust anyone. And now the question is how we do this thing, how we move this trust. We also discovered that when we just say this thing to people, it doesn't really hit the way in which they think. Like they are still kind of a bit lost engineers about how to reason about this. So what we discovered is that actually what we do as privacy engineers is a lot about another actually regulatory principle, the principle of purpose limitation. So when I write here, the usual approach is that the kind of approach that we have to build a system, and we, I mean, like the very broad computer science community. And you can see this already if many of you are actually professors of computer science or of similar discipline at the university, where you teach your students the first times they program, right? When they think about a program, they think, okay, I'm going to collect everything I have, and then I'll do operations with it. And that's also how people want to build systems normally, right? Think about something, okay, let's just collect all of the things that are possible, we don't care. And then it turns out that comes data protection and, you know, the regulation, there's this minimization principle, and, you know, you cannot collect everything you want because it has to be kind of associated with your purpose. So you end up collecting less data. And that's most of the systems that we have, actually anything that passes through the data protection funnel. But the privacy engineers think in a very different way. What we think is about first, what is the purpose of the application? Then we think exactly about what is the data that I need for the purpose. And then because there are other operational purposes, like you cannot build systems without, linking things together and creating servers, and maybe there are other legal requirements for accountability and things like that, and you end up needing to collect other things. There's also security, by the way, that we need to fulfill. So sometimes you may need to collect a bit more data than what is needed for the purpose. So you will collect a bit more, and to avoid that, the data that you have to collect more for these operational purposes is where we put privacy enhancing technologies to ensure that the purpose is still fulfilled. And as one example, back in the 2010s, we built this privacy as you drive scheme, in which we thought, like, if you have to pay for how much you drive, what is the exact data that you need? And actually, the only data that you need to pay is to know the final amount of the bill. The rest of the things that appear on a bill are in general actually kind of accountability and checks, but it's not the information that you need. And then that would be kind of the minimal amount. And to really build a system and to ensure that people could not cheat and all of those things, we actually had to create a log. The log had to be privacy preserving, so we had to encrypt it. And that's how we ended up with a system that had a bit more data than the amount to bill, but it's still much less data than any system that you would collect that would actually gather all of the GPS data for the vehicles and then maybe reduce it somewhere, but it would always be less data. So in this sense, the idea of limit the purpose from a technological perspective limits actually the need of trust, because if all the data I give you, you cannot use it for anything else than exactly the purpose I said to you, I don't need to trust you for that you're not going to misuse it. It's just going to happen. So this is kind of a good metaphor to explain to people how to think about privacy preserving system. And that made me very happy, right? Because now I have a way to teach my students about how to think in this complex way that took me like almost 20 years now of being working on this topic to really understand what is it that am I doing. And this is great. We have now something, we have a tool to reason about these systems. And this is actually what you see in most of the academic literature. But people, at the end of the day, the introduction of the paper says, this is the problem I have, this is the only data I need. And then they spend all of the rest of the section putting a lot of technical details to just convince you that they actually have fulfilled the purpose with very little amount of data by means of super cool crypto and other stuff. And this actually is very similar to what would be a waterfall software development, where you establish the requirements and then you design the system, you develop, verify it, deploy it, and maintain. And you can read this as, intro of the paper, section 1, system model, implementation of the system, like an instantiation, evaluation, and well, we don't deploy in again. But you see how this goes. But it turns out that in the world we live today, this is called the past. Nobody anymore actually uses this kind of waterfall, right? We now live in an agile world in which this idea that the requirement phase happens at the very beginning, and then you just, waterfall design and deploy, does not happen. Design is agile. The requirements change over time. And also, we don't live in a system where we control everything as we do on the papers, where we just control the full stack. I think now people deploy in this thing of as a service, deploys over services, in which your design is not only constrained with what you know and what you can do and your requirements, but it's also constrained by what these little blocks that you're going to use as a service, whatever is an app, it is a service, an authentication service, it is the cloud that is going to give you an API, and you're constrained by all of those. And those also affect your privacy capabilities, because if the API does not offer what you want, you may want to have excellent crypto, but if the API does not offer it, it doesn't matter that you know all about privacy preserving protocols, you just cannot build it. And underlying all of this, here in the infrastructure as a service, there is actually hardware. It is actually the chip that the infrastructure builds on, that the platform builds on, software builds on, and that also constrains what each of these elements can do. And just to show a little bit how the difference between having the freedom, like to be here as a privacy engineer, or not having so much freedom, let me talk about two projects that my lab developed in the last 2 years. On the left, we have Datashare. This is a decentralized search engine for investigative journalists. We had a 2-year collaboration with the International Consortium of Investigative Journalists, the guys of the Luxembourg leaks, the guys of the Panama Papers. And they came to us and they say, we have a ton of electronic documents and we would like to be able to search on each other's collection because we find it very useful, but we're very scared of putting them out there because they actually can get us killed, right? These guys have all of these leaks, like imagine if Snowden had just gone with the pile of documents and just put it on the search engine for everybody to look for things before he left, right? And we built for them a system that is currently being implemented, hopefully deployed by early next year. COVID pandemic always delays things. And here what we had is it was a complete blank slate for design, right? This guy said, yeah, you can build anything. We don't have an infrastructure. We don't have anything. So just you guys, which are the privacy experts, tell us what to do. And in the sense, we had a total control of the stack. I here put total quote unquote, because we still have to use the internet, which is not something that we can completely redesign from scratch. And also the journalists don't have their own clouds and their own things. They still use Amazon Web Services. So there are some things that we will limit. But because we had this total control and freedom, we have space to deploy any crypto we wanted. And in fact, we deployed very novel protocols for them and a new way of combining privacy preserving protocols to solving their problems. Because we also had a space to design a whole system, had a space to put anonymous communications there, anonymous authentication, all of it was great. On the other side, like for the last year and a half, I spent in this frantic design of contact tracing apps. And here we had to design very fast, and we had to design for something people already had on their pockets. And that meant that our design was based on existing components, right? Existing on the phone, the operative system, had to be existing on existing communication, so we had to use BLE. It turns out that BLE has a payload of 16 bytes. Well, off you go. Like all your crypto is actually limited to having 16 bytes of payload. Believe me, that limits a lot of the kind of fancy things we can do and the level of security we can get. We had to rely on the services that the mobile and the cloud gave us. Right? The moment that Google and Apple decided we're going to implement the protocol inside and give you an API that completely limited, like there was little space for our own crypto, we designed the protocol, they took it, they put it down, and that's the limit of our power. And also meant that the end-to-end design space was completely limited with what they said. Because if this API gets a signature and the signature is in the format that they want, you cannot now go fancy and use group signatures or anonymous signatures, or you have to use whatever they tell you, right? And all of these things actually completely change. So this is to say that whatever you put at the end of the day at the lowest level in the hardware is going to have an implication on what, how, and how much we can build at the top. So with this, I started my wish list of things that would be great to have, and that would be great to start having hardware that supports it, because that will also push up the stack, like in the platform as a service, in the apps as a service, more and more libraries and capabilities to use the things that we want to use as privacy engineers. And the first thing is, well, I really would like to have a hardware crypto Swiss knife that is actually tailored to the needs of privacy preserving protocols. And let me present you a couple of cryptographic tools that we use very much to use privacy preserving systems. And because I'm not a cryptographer, I'm not going to embarrass myself going into details of the crypto, but I'm just going to give you pointers to what are the names of these technologies, what are these key keywords that if you're interested in building technologies for this, you can go and Google and find it in different general security conference or privacy conferences, and then you will find the details of the crypto. And I trust you guys that you're the best at actually taking any crypto and put it on a hardware implementation. So the first one I want to talk about is privacy intersection, which allows us to actually learn about the intersection of two sets without learning about anything else that is not in the intersection. We can even go further and just learn the cardinality of the intersection, even without knowing what are the elements in the intersection, let alone elements that are not in the intersection. And this has a lot of applications for private content discovery, like for instance, WhatsApp contacts, like who are my contacts and what are the numbers in the big database of WhatsApp. Private search. This is actually what is underlying Apple's CSAM, very controversial detection. Happy to talk about it on the Q&A if you are into that. It is actually what is behind our design in Datashare. It can be used for intrusion detection so that two companies can compare their intrusion logs without and learn what are the common attacks without knowing anything else about the rest of the logs, and has many more applications. And this kind of private set intersections, they are either based on modular exponentiation and VCC. There's a lot of hashing, not necessarily the most common hashes. That depends on how exactly you want to build. Some of them build a multi-party computation, mostly two-party computation, because in general, these are thought about two parties building an intersection. Some of them are based on oblivious PRF, which of course built on hashes and ECC, but built in particular ways. And because when we build these protocols, we not only think about the hardcore crypto, but also that we need to put them on a system. And on a system, we need to make sure that all of this is efficient and works. And a bunch of these things are not efficient at all. And because we don't have hardware acceleration or anything, they're just not efficient. We need to use other tricks. So one trick very common with private set intersection protocols is the use of cuckoo filters, which are the clever brother of the Bloom filters, if you want to see them like that. And we use those for efficiency, communication, and speed. Now, maybe if we're going to have more acceleration on hardware, we don't need the trick anymore, but maybe you do. So actually the input to the protocol at the hardware level is not going to be messages as you would think. It's actually come in a different format. And also we do these operations, but running the whole protocol, it doesn't require one exponentiation. It requires one per element in the data set. So we need to run these little primitives here, but we need to run them many times in order for this to actually work. And these are the kind of things that when we just think about the primitives, we may think about, okay, I'm going to make this faster. But sometimes it's not only about making them faster, it's also about thinking what is going to come surrounding and kind of co-design those in a way that the whole protocol is actually efficient and fast, which is actually what we need to be able to put them on our systems. Then we also have private information retrieval, which allows us to retrieve an element from a database without telling the database which element we retrieve. And this can be used for private messaging so that you can retrieve messages from a mailbox without telling the mailbox which messages you're interested on, for certificate transparency so that you can retrieve which certificates you want to check without telling the database of certificates which thing you're browsing, for private media browsing, for many of these things. And there are two flavors of private information retrieval: computational, which is actually securities based on computational assumptions, or information theoretical, which is about distributing sets and distributing the data on several servers and then do some operations. Information theoretical is more secure because it's information theoretically secure. But you know what? I love all of these multi-party computation things. But when you want to deploy in reality, there are so very few moments where you actually do have non-colluding servers. I'm sorry, guys, I'm sorry to break this to you, but in practice, this very rarely happens. For instance, in the project with the journalists, right, where people were like, oh, why don't you use super fancy MPC? Like, because these guys don't have two servers. Like when we talk about this possibility, they said, oh, yeah, we can spin two instances on Amazon. I was like, it's not gonna cut it, right? But you cannot expect that different journalists in the world, they actually have one server, one in each jurisdiction, right? One in Brazil, one in the UK, and I was gonna say one in Canada, but it's kind of the same. One in China, they don't have that. They only have one instance in Amazon Web Service. So when you go for deploying these things, you mostly go for the kind of one server thing, even though there's a lot of literature on the rest, but you know, that is the one that actually can hit reality. And protocols of this sense are based mainly on homomorphic encryption. There's some fancy that use something else. And that means that we mostly need lattices, right? That's how homomorphic encryption is built nowadays. And there's very little support for lattices on hardware. And again, here, to make all of this efficient, we see how people use, again, a lot of strategies to represent data in a different way, like stacking and batching, so that they can compute many things at the same time, because it will require many operations on the server side. Remember that you don't want to tell the server what message you have touched. And this already gives you an idea that you're going to have to touch a bunch of them if you really don't want to reveal which one is the one of your interest. So you're going to have to do many operations, and these operations are expensive. So either due to this packing and batching, or people nowadays are moving to offline phases of pre-processing. And this is actually also very interesting, right? Because it tells us that we have in many privacy preserving protocols kind of two phases. One phase where maybe we don't care if it's so energy efficient or so slow, because it's going to be offline, right? So we can actually spend maybe more time doing it. Maybe we want to be very energy efficient, but we don't mind if it is for one day you have to go pre-processing all of these things, because it's a one-time cost. But then you need something very fast online. And these kind of two separated things may actually result on very different hardware designs, but both of them are going to help when combined to actually allows us to use this kind of primitives very well in the wild. Another one that we use a lot is attribute-based credential, because it allows us to do anonymous authentication. Look, we can build end-to-end privacy preserving systems without having a way to authenticate, without having a way of actually preventing malicious users from coming into the system. And a way of doing this is using this kind of technology that is mainly based on zero-knowledge proofs and green signatures. Sometimes it's an or, sometimes we can get away with just doing the blind signatures. And this allows to prove in zero-knowledge that you're actually an authorized member. And to do these proofs, we need to do a lot of operations, again, either modular specializations or the curves. We again use a lot of hash functions. And recently, we use a ton of bilinear pairings. Bilinear pairings are starting to be the kind of the core of most privacy preserving protocols. They have very nice properties that allow them to be very flexible, and we can construct very nice kind of proofs with them. But they are also very expensive and very hard to program, and it would be great to have an abstractions. When we have attribute-based credentials, kind of the very basic is to just prove one attribute. I'm a member of this thing, I'm older than 18. But actually, there are very fancy protocols that achieve cooler things like the capability to revoke. Again, you think about building end-to-end systems and deploying them in reality, revocation is a must. Limited usage, so I'm going to give you an anonymous credential, but you can only use one time or two times. And again, each of these things kind of come with a little bit more crypto, and each step is great. It allows more functionality, but also makes them more prohibitive to deploy in practice. And here we have something that, as opposed to before, we don't require many operations. Only one operation on the client to construct the proof, only one operation on the server to verify the proof, but both of these are expensive. Depending on the anonymous credential and the zero-knowledge proof, it may be that you put more weight on the client, on the server, or you distribute, but at the end of the day, one of them is going to be expensive. And therefore, this kind of technology is kind of hard many times to put out there, especially if we are going to put them in smart cards that really don't have much but up. And there are many more of this crypto that we use. I just gave some examples of the ones that are very much used, and that if you see systems, kind of all of them tick many of this. But all of the other fancy protocols, at the end of the day, the underlying building blocks, like the primitives, you saw that in my 3 examples, I already started to repeat what are the needs, are mostly common. At the end of the day, all of them have the same structure, but the same primitives. They're used in slightly different ways, but it's not that we have infinite of them. And that also means that the bottlenecks are common. And if you want to know more about how this is used, go to the Precedence of Paths, Usenix, CCS, SMP. And I encourage you to not to look at the crypto papers there, but actually look at the privacy preserving systems in those papers, and see how they use these protocols, how they combine them to really understand the needs beyond the crypto itself. So, okay, we have to these things. So why there is no privacy, right? They have said before, it's because it is very hard to deploy them in privacy. They are based typically in non-standard use of cryptographic primitives. like I have mentioned, it's not that other people don't use ECCs, not that other people or other schemes don't use modular exponentiation, but this is a non-standard use, and therefore we cannot use the implementation that are out there. So they end up, they're mainly academic primitives that nobody really works on in the real world. So there are very few software libraries, and the ones that exist, they need to build from scratch because there is no hardware support. There is nothing underlying them. They have to implement all of the little things. They end up being slow. And also, these libraries, sadly enough, they have suboptimal support because they are not built really by companies. They are mostly built by academia. And either they are very slow, because there is no hardware acceleration. We need to do everything in software, and these operations are very, very expensive because hardware acceleration mainly focus on the mainstream, AS, RSA, also ECC, but on these particular use cases, that I'm sorry, it's not what we need. It's not how we use those primitives. And actually, if you look in the literature, there have been people actually kind of misusing sometimes these APIs. So you can actually take an RSA accelerator and misuse it, quote unquote, the API to actually build fast anonymous authentication. But we wouldn't like to have to go and reverse engineer how these things work and find a way of misusing the APIs. It could be great if we have APIs that actually allow us to build privacy preserving systems. And many of these primitives are also very energy consuming, and there is no efficient implementation because there is no way we can do this only in software. And that means that they become absolutely prohibitive to put anywhere that you actually don't have a power cord on it, like the Internet of Things. So what can you do for us? What would be great? Build hardware support, right? Build accelerators for this kind of uses of primitives, or for the primitives that so far don't exist, like bilinear pairings. It would be great, right, if we could have some of those. And when you think about building this hardware, think both about putting it on the normal processors that we have in commodity devices, because we want to build these things on the phone and on the laptop, but also think about how can we put it in independent devices. Because as I said very early in the talk, right, one of the things that we don't want, where we want privacy, is to avoid the power that others can accept on us. And would you only put all of these primitives on the mainstream devices, it actually means that the privacy engineer is still under the control of the operative service provider. And this is the example of the contact tracing apps, right? Even if you put there, at the end of the day, they are going to be the one that show the API to us, and we're still going to be limited. So it's great if we can start to separate and build independent devices that allow us to actually escape from the control of the Googles and the Apples and the Microsofts of the world. And then let's build some energy efficient implementation so that we can put this, I mean, even for phones, right? As you will know, everybody hates when the battery is drained very fast. And some of them, we're going to need them fast, because some of the protocols we do actually are for real kind of real-time implementations, or that have speed constraints. Again, contact tracing app is an example. Some of them, we want them small and very efficient, right, for this IoT of online phases, or we just want them to be not consuming very much battery, but we don't really care about the speed. Like when we built this thing for the journalists, as opposed to other PSI protocols, like the main thing for contact discovery, for instance, on WhatsApp, is how fast you can go through this huge list on the server of contacts. The journalists don't need fast, right? They want something to search, and waiting for one day to be able to search on all of the journalists' collections of the world, that if you don't wait, you just can get zero capability to do that, is perfectly fine. For many privacy-preserving applications, speed is not actually a constraint. And it's, again, I think, a way of going back and thinking about what is the purpose of my application and what are the requirements, because we're many times nowadays very, very oriented by the goals of the Googles and the Apples, of the big tech that tells us, what are the needs. And they actually want to do real time, and everything for them is kind of large scale. But many people that actually need privacy are a much smaller scale, and they are not always in a hurry. So actually building for different trade-offs can be extremely useful when you talk with privacy engineers. And for some, we're not. I'm here with my wish list. We want both, fast, small, and very efficient. Off you go. And please, 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 when you're going to do all of these things, ensure that you talk with developers, ensure that we talk with the people that are going to use it. When deciding what kind of abstraction you're going to offer the exterior, how are we going to be able to use it? Because I'm sorry, if we cannot program, it does not exist, right? We cannot use it. It's just useless. But there are many people that are really looking forward to these technologies and they would love to spend a lot of time with you actually learning about your discipline and finding how to code assign to actually really bring these things to the market, because that's the only way in which we can really have privacy at a broad scope. Okay, so you imagine that you gave me this thing, and yeah, I now have my Swiss knife of hardware crypto cool stuff. Are we done? Like, no, I'm sorry, not done. Crypto is not the only thing. Encryption and confidentiality is not the same thing. But now at least we can start to build systems. We can start to have these primitives that allow me to compute it in the encrypted domain and build systems with them. And that means that we're going to use these primitives in different ways. We already talked a lot about batch operations. And why these batch operations happen, let me remind you, is because it is private. So many times we either don't know which record we're interested in when we do something, like in private settings section, or we don't want to show which record we're interested in, as in PIR. And that means that we need to repeat our operations many times. That means that when you're thinking about hardware about this, maybe you just don't think about the entrance that only gets you one message. Maybe think about something that allows me to compute in batches, that already gets that embedded into the hardware design, that could actually allow to accelerate a lot the kind of things that we do, and may actually, if you do this kind of in co-design with the people that do the protocols, it may really, really make the use of this primitive so much easier, because we can abstract on some of the things that right now we actually need to program in software, and it could be great if we could forget about it. But also, we not only have these places, we just need to compute on a full database. A very much used trick that we have on privacy preserving design is that we use a lot of trial decrypt. And it is because the fact that it is private not only means that we don't know what message or what record we want to attach, it also means that we don't know what key to use. So we kind of need to try all of them. And to give an example of this, in contact tracing apps, so first we have the Bluetooth. But we now have an extension that allows us to do what we call presence tracing. And this is to kind of be able to alert people that have been sharing a space, like a restaurant, a bar, a room, a meeting. And for this, what we do is we put a QR code on the venue that these people are going to be in. This QR code essentially contains a public key. It's a fancy privacy preserving public key kind of thing, but for all intents and purposes, this talk is a public key. And then when users come, they scan the public key with the phone of the cameras. And then when eventually it is discovered that this restaurant had a positive and we want to launch an alarm to everyone, the doctors contact the restaurant, give them an access code, and then they can upload the secret key of this QR code to the server. All phones go and collect all of these secret keys of all services. And now they have a list of public keys they have scanned and a list of secret keys that some of them are that denote that there was an infection. So now we need to go and try all of the keys in all of our public key scans to see if one of them actually decrypts. If you decrypt, you actually have been there. But the only way we have is to actually try this, right? So that means that we not only batch cipher this, we also batch keys. And believe me, this is a thing that we have to do many times when we design. And we get to this quadratic explosion that actually, again, bumps our energy efficiency, works our fastest time. In this case, for the phone, right, mostly we're caring about energy efficiency, the fact that we don't drain the battery of the phone, and this is kind of problematic. So if you can find us another way of building hardware that actually also thinks about the moment where we're going to receive many keys, that'll be cool. The good news is that the constraints here are also kind of a bit more flexible. It can be probabilistic, this decryption failure, right? You can end early if you're kind of almost very sure that this is not going to happen. That means you can abort early. To be fair, we're not really sure whether timing attacks how much they would affect here, but I've heard that the people in the chess community are actually experts on timing attacks. So I hope that you guys can work a little bit on it and give us like what is the good trade-off here for the risk they have in the timing attack, but the advantages that it gives me on the implementation side. We could also use some plain text, right? I mean, that depends on the privacy situation. You can have a trade-off, but we could also imagine situations in which we could give some hints so that you don't need to test all the keys on all the ciphers. We can talk about all of those things. But at the end of the day, we're still going to do trial decrypt. We're still going to need to repeat this operation a zillion times with different keys. So that's another thing we use a lot. And another main difference that I think that sometimes is not really seen about how different it is when you design the hardware and when you design the whole system, in particular from a privacy preserving way, is that at chess, like most of the things are really on this chip. Like the adversary is looking here very close to the chip and can talk to it. But when we design a privacy preserving system, like chips are part of devices, and we actually assume that the adversary is kind of everywhere, right? It can look at the devices. It can also look at the chip. It's not that we forget about this thing. It can look at the cloud. It can look, essentially, it can look everywhere. And what that means is that maybe the adversary cannot do the attack here, and you may think, well, that was my job. But the adversary may do the attack here, right? And that means that what I said before, like encryption is only the first step to achieve privacy. And you're not done, we are not done to encrypt things. And this starts to be very, very relevant in the world of the Internet of Things. And here is a paper from my colleagues at EPFL, where they were studying Bluetooth wearable devices, particularly kind of fancy Apple phones and things where you can install apps that interact with your phone and do a bunch of stuff. And a lot of these apps are actually very sensitive because they have to do with health, or they have to do with church. Like there are apps that remind you when to pray. There are apps for everything. So what they show here, right, is that when you have that thing, the adversary may not be actually on the phone, may actually just be at the network, looking at the encrypted communication, and then like a good adversary will just look at this, look how the packets look like, and then it is able to identify sensitive actions. And it is able to identify actions like to a very large extent. Here we have a precision matrix. This is what the adversary predicted. This was the true label. And we see that the adversary makes very good errors, right? The probability of having the predicted equal to the true is very high. The rest is fundamentally white. Only when there is very low volume applications, when there is not enough traffic, the adversary is not able to do this distinction. And the things that they showed, extremely privacy invasive. Like, yeah, you can design whether there is a measurement, you can see for applications that are about when you eat, whether there is food intake, when you send messages, receive messages. And I just took another example from the paper to show that you even, like this is an application for diabetic people to actually kind of take notes of how they're doing. And the application says everything, right? When you are eating food, what kind of food you're eating, how you're doing. And then they say when you add glucose and when you add insulin to just kind of keep you on track. And this guy showed that you can essentially distinguish everything that happened just by the traffic. And how we typically solve this from a privacy preserving perspective is to use dummy traffic that you may also have heard about as chaff. And the goal is to hide information from this network observer, to hide these patterns, because otherwise, I'm sorry, the Internet of Things is never going to be private, because we're going to be leaking a lot on what these things are sending to the router, to the phone, to whomever they are sending. And the signs that work on dummy traffic, they do one or more of these things. Either they add packets at random intervals, and what is the distribution of this randomness actually matters a lot. Happy to have a whole discussion about how hard it is to get it right. Or you can add packets, not kind of from a random distribution, but actually to mimic other applications, other actions, right? You just try to mimic, you just try to hide in the crowd. And the thing about all of this is that it has high cost, because you need to compute more things, you need to compute when to put these things out. You're going to consume bandwidth because you need to put, and it turns out that bandwidth consumes energy. You're also going to have to wake up at moments that typically you don't have to wake up. So you're going to augment the number of times that the phone or the device, the IoT device, has to spend battery, has to actually pull, I can come on and take the big energy spike from the battery. And that means that at the end, they're rarely deployed. But as I said, without them, we're not going to have end-to-end privacy preserving systems. So what can you do? And this maybe is kind of my wildest dreams, if these are possible. Can we reduce the energy consumption? If you guys think about the fact that this is going to happen, the fact that there are going to be more messages than what you think, the fact that we're going to have to combine network privacy with computation privacy, when we do something that allows these devices to be more energy efficient, can we maybe just create the dummies at the hardware level? They just need to be random, with some particular randomness, but maybe we can configure that. And also the timing, their timing is kind of independent of real traffic. That's the whole point, right? If you make the time independent on the real traffic, that means that also the dummy traffic is going to leak information about the real one. So maybe we can actually just create chips that do that for us. And maybe those are much more efficient than actually the kind of things that we have nowadays, when we have to do it at the application layer. And then we have to reduce a lot of things that are very non-efficient. And again, I would like to remind you that sometimes the speed is not a requirement. We can afford very slow, efficient computation, maybe over time. We can sometimes even afford very slow transmission over the network because, we're not in a hurry. So maybe we can find ways in which actually the network interface is used by the hardware in a way that allows us to put more traffic on the line in a slower way, but actually gets us to have very high privacy at a low cost, so that we can actually convince vendors of these small devices or vendors of phones that actually we need to protect the traffic because otherwise we're lost. And by now you're thinking, well, why does this person come to ask me for crazy things that we cannot do? The good thing is that negative results are also great. Okay, if you tell me that there are limits on the hardware state, that we're never going to get research that shows the limit of privacy are as important as solutions. We move forward in this digital world on the assumption that we will fix it later, right? You can see this with machine learning fairness or with optimization or in general with privacy, right? It will come later on. We'll build it and then later on we'll plug something in. It is very important to inform policy discussions about the snake oil that they are being sold when people tell them that this will be solved, that we will solve the ethics of AI. You just need to wait for a couple of years until someone in Europe comes up with the algorithm. No, we are starting to have more and more negative results there that show that robustness cannot coexist with fairness, or that privacy cannot coexist with robustness. And these things are so important because otherwise policymakers that are lobbied all the time, they will believe that the Holy Grail will appear and it will solve all of their problems. And by the time they realize this is not the case, we will have a world in which privacy is not possible anymore. So if you have negative results, bring them to the table. I would also be happy to take them on and to also write on our papers like, well, this is the limit of what we can do. And now we have to choose in which kind of society we want to live. The society which maybe has that application, but will never have privacy, or the society which, maybe we're a little bit less digital, but we do have privacy. That's kind of nice. So with this, I would like to end my talk and to just kind of refresh the key points. What we do when we do privacy is to actually limit the purpose of the systems that we create so that we don't need to trust anyone to use the data beyond that purpose. And for doing that, we need to use bunch of non-standard cryptographic and non-cryptographic solutions like the dummy traffic. And these are constrained by the infrastructure. And the infrastructure includes hardware. And sometimes help starts from the bottom. And if you can kind of help from this bottom by producing more and more efficient things, it will be easier that actually those improvements get to the software layer and we're actually able to deploy this thing. So we need better support. And if you cannot build it, find the limits. And this is equally important for the actual discussion at the broader level. And with this, I'd like to stop and take questions, which I hope to have many, and learn more from you than maybe what you have learned from me today. Thank you very much.
Thank you so much, Carmela. It was a great talk. So we have so far one question in the Zulip chat, and I have a few more questions. So one question is about homomorphic encryption versus multi-party computation, where the question says that the Confidential Computing Consortium claims that there is an ambiguity in the definitions of homomorphic encryption and multi-party computation that leads to gray areas between the two concepts. And the question is if you have any thoughts on this.
I think that can be probably correct, right? That sometimes multi-party computation is, you could really call it homomorphic encryption in a way, because you're doing like the kind of techniques you use, they are so close to each other that probably they are the same. Now, from my perspective, or maybe in the context of this talk, this is even better news, because it means you guys may only need to do one of these to actually, two birds with one stone. You can help us do multi-party computation and homomorphic encryption with the same piece of hardware. It's even cheaper and better.
Thank you. There's another question. To what extent does privacy require secure hardware or a secure system? Ultimately, you don't have a security on a compromised system, but perhaps state-of-the-art systems sufficiently minimize data stored on the user's device to, for example, survive later or temporary compromise?
That's a very good question. No, in many cases, I don't think we really need secure hardware, like anti-tampering hardware, like the adversary model. I said that in my picture about the two adversaries, I said the privacy also cares about attacks that you can have on the chip. It does in the sense that, especially when we outsource to the cloud and we don't trust the cloud at all, we also don't trust that the cloud, which is very powerful adversary, like the cloud provider, cannot maybe do a hardware attack there. But as this person says, maybe on the phone, physical security is not the priority. But again, like the fact that the hardware is not secure doesn't mean that the hardware cannot help securing the network. You see what I mean?
Thank you. Another question, hardware-based trusted execution environments are also emerging as a solution for privacy-preserving scenarios. You did not talk about those. Did you imply that TEEs are not important or will not be dominant in the future?
Crystal balling is not my forte. So I think the TEEs are interesting. They are very useful. They sometimes enable to even kind of offload some of the heavy computations of all of these protocols, kind of the TEE, and you can make hybrid approaches. So there are two things. One is that, yeah, TEEs maybe, but not all phones have TEEs. And in general, TEEs are also very restricted in access. Again, as we were talking about that before, right? Phones have TEEs nowadays. Do you know how many can I use to build my privacy-preserving applications? 0. So that is not going to be kind of the solution that brings privacy or privacy engineer, I think, to a broader scale. It kind of actually still leaves the privacy engineer in the hands of the powerful, the Google and the Apples, that are going to decide who, why, and when can use the TEEs. It also is still a kind of technology that depends on maybe the hardware manufacturers and how they do these things. So I don't know. I think that we need to move both at the same time. But in particular, what I don't believe is that everybody's going to have access to a TEE, and so we need other ways to get access to the privacy that the TEE would give, and this is actually this purpose.
Okay. I have one question actually, which is, so you're saying that privacy is about minimizing trust. And I think as, well, when looking at cryptographic protocols, whenever we eliminate more and more trusted parties to ideally have none left at the end, we get a problem with usability. So usually systems where we trust some parties are much easier to use. Like one trusted central party already simplifies a lot of authentication issues, key management, and all of these things. So how much do you think this is an issue that if we're building more and more privacy preserving and trust minimizing systems, that the average user isn't using them anymore or can't be using them anymore?
Okay, I don't think that the usability, when you were saying that, I was thinking that you were thinking about the usability for the developer, which indeed is a freaking nightmare, right? Every time we decentralize, we need to go around doing a lot of stuff, and it is hard. It's hard to get it right. But for the user, it's not that these things really kind of make a big difference right now. The question is, can we abstract this away from the user? Like, I don't understand why having a decentralized system essentially makes a difference from the point of view of the user. For example, in the contact tracing apps, users have no idea whether the thing is decentralized or not. In fact, they could not distinguish a decentralized from a centralized thing, but because for them, there is a phone doing Bluetooth and sending stuff to places. So I think you're very right that privacy preserving technologies make developers' life much, much harder. I'm not so sure that that necessarily goes to making the user life so hard. And also, I mean, thankfully enough, there is a lot of research that goes actually on usability of privacy technologies, and we probably would need more, but I don't think that those things are kind of fundamentally impossible to put together.
Okay, that's great. One more question. Can you maybe elaborate a bit on when you mentioned in one of the slides, can't build end-to-end without authentication?
So when we want to use these privacy preserving schemes, and we have a lot of, for instance, privacy preserving search, right? And privacy preserving search, it's at the end of the day a leaky primitive, because you're always going to leak one thing, what you search for, right? If you search for something and you find it, you can receive it. Now, the only way we have to avoid that is to avoid that somebody can come and make infinite queries. And for that, we need to know that people that came, but that the people cannot do infinite ones. And the ways we have to solve those things are then to bring authentication. Now, when we have authentication, we're losing a lot of the privacy problems we had before, privacy properties we had before. So we want to do anonymous authentication. That is one case. Another case is for abuse of systems. Like many times people like Wikipedia, for instance, would like to be able to actually limit how much abuse there is. And they do this by doing a straightforward authentication. And if you move to the privacy preserving world, then you would like to have some kind of anonymous authentication that allows you to say, I'm a legitimate user, right? That is not doing bad things. And that's the kind of thing you need to prove. But why we need all of those is because if we ask Wikipedia to go anonymous, then they ask us, give us an abuse prevention system. In the case of the search, it's the same kind of thing. So maybe what I'm saying is that we need authentication for prevention, and then we need to bring that, again, take a step back and put that prevention in a privacy preserving way. I think that's what I meant. I don't know if I make it better or worse.
I think you made it better.
Okay.
Also, I think we have 2 more minutes until the next session starts, so I'm afraid we have to stop here. So thank you again very much for this great talk. I don't know if you can join Zulip to maybe answer some more questions that are popping up. Then maybe we can continue the discussion there and move over to the next session. Great. Thank you again so much.
Thank you.